In this video, we're going to look at another example of separable differential equations. The question here is to solve the differential equation y prime is equal to x cubed log x divided by y with initial condition y of 1 equals -1. The first thing we should consider is this a separable differential equation? So y prime, we can write it as dy dx is equal to x cubed log x times 1 over y. So now we have a product of a function of x, which is x cubed log x, multiplied by a function of y, 1 over y. We have written dy dx as a product of a function of x times a function of y. So indeed, this is a separable differential equation. So let's do the calculations. Dy dx is equal to x cubed log x divided by y. So now let's cross multiply so we can separate out the variables. So we get y dy on the left hand side. On the right hand side, we get x cubed log x. We have now separated the variables, so now we can carry out the integration. So you should always do this step first. You have to put all the y's on one side, all the x's on one side, so you can integrate both sides independently. All right, so let's integrate the left-hand side and integrate the right-hand side. Well, the left-hand side is pretty easy. If we integrate that, we're going to get y squared over 2, reversing the power rule. But the right-hand side is a little bit harder because we have to apply integration by parts. So recall integration by parts, integral u dv is equal to uv minus integral v du. We let u be equal to the log function, log x. Differentiate both sides, we get du is equal to 1 over x dx. We let dv be the polynomial x cubed dx. And integrate both sides, we get v is equal to x to the 4th over 4, reversing the power. All right, so we get y squared over 2 on the left-hand side. On the right-hand side, we get u times v, which is log x, times x to the 4th over 4. uv minus integral v du, x to the 4th over 4, times du, which is 1 over x, dx. Okay, let's simplify this and integrate. So what we have is y squared over 2 is equal to log x times x to the 4th over 4 minus integral v times du, x to the 4th over 4 times du, which is 1 over x, dx. So we get y squared over 2 is equal to log x times x to the 4th over 4 minus 1/4 is a constant, passes through the integral, so we get minus 1/4 integral, and x cancels with x to the 4th, gives us x cubed on top. So we get integral of x cubed dx. So we get y squared over 2 on the left is equal to log x times x to the 4th over 4. Now reverse the power rule and we get x to the 4th divided by 4. Add 1 to the exponent and divide by the same. Plus constant of integration c. Now let's multiply both sides by 2. We get y squared is equal to 2 over 4 is 1/2, so we get log x times x to the 4th divided by 2 minus 2 over 16 is 1/8 minus 1/8 x to the 4th plus 2c. All right, so let's rewrite this as y squared is equal to log x times x to the 4th divided by 2 minus 1 over 8 x to the 4th plus c1, where c1 is equal to 2c. Now let's square root both sides and solve for y. So we get y is equal to plus or minus root of log x times x to the 4th divided by 2 minus 1 over 8 x to the 4th plus c1. All right, so we have y is equal to plus or minus root of log x times x to the fourth divided by 2 minus 1 over 8 x to the fourth plus c1. We have an initial condition y of 1 is equal to negative 1. Now the question we have to consider is which of these two solutions should we accept, the plus version or the negative version, the minus version? We're going to choose the negative version because it matches up with the initial condition. Y of 1 is equal to negative 1. The y value is negative. So we have to choose the minus version. So y of x, so we match it up with the initial condition. Minus root of log x times x to the fourth divide by 2 minus 1 over 8 x to the fourth plus c1. So we have y of 1 equals negative 1. This means when x equals 1, y equals negative 1. So let's plug in negative 1 for y and 1 for x and solve for the constant c1. So on the left-hand side, we get negative 1 is equal to minus root of log of 1 times 1 to the fourth is 1 divided by 2 minus 1/8 times 1 to the fourth is just 1 plus c1. Now recall that log of 1 is equal to 0. So this simplifies to negative 1 is equal to minus root of log 1 is 0, 0 times 1 is 0 divided by 2, that's all 0, minus 1 over 8 plus c1. All right, let's square both sides. We get 1 is equal to, we square both sides because we get rid of the radical, and we get negative 1 over 8 plus c1. Add 1/8 to both sides, solving for c1, we get c1 is 1 plus 1/8, that's just 9 over 8. All right, so we have simplified this to y of x is equal to minus root log x times x to the fourth divide by 2 minus 1 over 8 x to the fourth plus c1. And we solve for c1. c1 is equal to 9 over 8. Let's plug it in. And we have now the explicit solution y as a function of x. Y of x is equal to minus root of log x times x to the fourth divide by 2 minus 1 over 8 x to the fourth plus 9 over 8. So the big picture is that we were given this question, dy dx is equal to x cubed log x divided by y, and the initial condition y of 1 is equal to minus 1. And we applied separation of variables, and we came up with this solution. Now, when you have a solution, it's a good idea to try to debug for mistakes, because we all make mistakes. So the trick here is we're going to just check to see if it satisfies the initial condition, y of 1 equals negative 1. It's not a complete check, but at least if it doesn't match up, we'll know that there's a mistake someplace. All right, so y of 1 equals negative 1. We get minus 1 for y. Is minus root of log of 1 times 1 to the fourth is 1 divided by 2 minus 1/8 plus 9 over 8. And what do we get? On the left-hand side, we get negative 1 is equal on the right-hand side. Log of 1, that's just 0, so we get 0 minus 1/8 plus 9/8. 9 over 8 minus 1 over 8 is 8 over 8, which is 1. And there it is, and we have a negative in the front. Negative 1 equals negative 1. So we just did a partial check just to see that it satisfies the initial condition, y of 1 is equal to negative 1. And this is just a good strategy for discovering arithmetic mistakes or algebra mistakes that you might have made along the way. All right, thanks.